Okay, so let's start our discussion with some basic concepts of vectors. We discussed why vectors are important in the previous segment, and in this segment we will start with formal um, usage of vectors and some concepts which are generally neglected by students while studying them, and then but they are really important. Okay, and one such concept is the difference between um, equality versus equivalence. Of vectors. Say suppose this is A, this is B. So how do you distinguish these two words as far as vectors are concerned? When do you say that two vectors are equal, and when do you say two vectors are equivalent? And is it important to even be so specific about this difference? And answer is yes. You should know exactly when to use the word equality and when to use the word equivalence. Now, to define the equality of two vectors, you do not have to, in fact, think anything other than just dispassionately have to think about the definition of vectors. How do you define a vector? You tell that okay, a vector is a quantity which should have a magnitude, okay, a direction. So, and we will later on we will discuss that in fact okay now along with that, for something to be called as a vector, you also require that it should follow all the laws, you know, of addition and scalar multiplication. Okay. Now, when some quantity, some physical parameter has these things, then you call it a vector. Now, and one more thing which I would like to add here for equality is that the dimension, okay. Now, when you compare two vectors for their equality, you have to look at this, this and this. If these three things, obviously when you are saying it is a vector, this will anyway be there, right. So, you do not have to bother about this term or this property of vectors which has to be obeyed anyways when you are calling it a vector. But now in comparison, when you compare a vector A with vector B, they have these three things should match. Okay. Now let us okay, for example, let us see, let me draw an axis, set of axes like this. Okay. For example, suppose this is x axis, this is your y, this is your z. Now on this, suppose you have a vector here, a green vector, I will call it say A, okay, and then there is a purple vector here, okay. I assume that or let me redraw it, okay, yeah. Now this is a purple vector B. They are completely situated at two different locations with respect to this origin O, okay. But both of them have the same direction, both of them have same magnitude, you assume that both of them are of equal length, and they live in the same three-dimensional world, which is represented by this axis x, y, z. Okay. And then maybe another vector I will draw, a light blue vector here, maybe where do I do? Say here, okay, at the origin. Now all these three vectors, they are exactly equal. So let's call this C. So A is equal to B is equal to C, because all of them are having same magnitude, same direction and same dimension. Okay. So you don't have to think about anything else. Now then what is equivalent? Are they equivalent? Now to answer this question, you have to ask one more question, okay, that under what effect, under what parameter basically, or what is the criteria under which you are comparing them. Without that there is no equivalence, and for equality you do not require anything, just dispassionately you have to tell that okay, if direction, magnitude and dimensions are same, two vectors are equal. Where they are, what they are doing, what they represent, it is immaterial. Okay. Then but for equivalence all those things will come into picture, what they are doing, what they are representing, and what in short you have to ask what is their effect. So I'll just say that equality is by definition, okay, but equivalence by effect, because they will do something, right? They are physical objects, physical mathematical objects, but representing some physical parameter, they must be doing something. Okay. So what is the effect? Now if the effect is same, then two vectors will be called equivalent. Okay. Let me give some example. For example, let us see, suppose you have a cantilever beam like that. Okay. Okay. This is called a cantilever beam, and which is fixed to the wall on one side. You might have seen that over the window sills and all. Okay. So this is a beam, and now you have say a force here, F1, and say another force, say let me take a purple color at this, which is F2, and this distance is say L, okay, and this distance say is 2L, and you have F2 is equal to F1 by 2. Okay. Now under this situation, look at them. Are these vectors equal? Are F1 and F2 equal? Are F1 and F2 equivalent? Okay. Now to talk about equality, you just have to look at are the direction, magnitude and dimensionality same. Now assume that it's a 3D problem, cantilever is in 3D space, so it has both the vectors have 3 dimensions or 3 coordinates to represent them. and both are downwards, but wait, the dimensions are matching, the directions are matching, but what about the magnitude? Magnitudes are not matching. F2 here is F1 over 2, it's half the magnitude. So obviously these forces are not equal. Okay, no, but are they equivalent? Okay, now as soon as you say that, or somebody asks you that are these two vectors, these forces equivalent, then this is actually a half baked question. It's not a well posed question. You should immediately ask for a clarification on the question, saying that okay, equivalent from what perspective? Okay, if you are thinking about the moment or the twisting effort which these forces are creating, then maybe they are equal. For example, let's see, now how much twisting effort or this force F1 will act at this end of the wall. It will try to bend it, right? So it will try to twist it, and that will be the moment of this force about this point, which will be equal to, say, let me say this is a moment due to 1 is equal to F1 times L, but moment due to 2 or moment 2 due to F2 is equal to what? Is equal to 2 times L, but F2 here is F1 over 2 times 2L, and these two cancel out, you get F1L. That means the moment that these two forces produce at this point, they are same. So if we are bothered about that moment as our effect, okay, you remember this word, this effect. Under this effect, yes, these two forces are equivalent, but if you change the effect, suppose somebody is thinking about how much reaction force the wall is now providing to keep it intact. Okay, the wall is actually keeping a action and reaction, right? Reaction force. Now how much is that force in, suppose when F1 only is there, the reaction also will be F1 and in upward direction. Say I'll just put this is orange color. So F1, let me put that in dotted to represent its the reaction force minus F1. Similarly, if only the F2 force is applied, then it will have a reaction force of F2 magnitude, F2. So the reactions will be different based on whether F1 is applied or F2 is applied. So that means if the effect which you are bothered about is the reaction force and not the moment or not the twisting effort, but the pushing effort, if that is so, then these two are not equivalent. So then to answer this question like this, it depends. Okay, for moment, yes. For say reaction force, reaction, no. So that's what, so the equivalence is a lot more subtle thing. Okay, you have to think a lot before you can answer whether two forces are equivalent. But to talk about equality, nothing. You just have to look for magnitude, direction and dimensionality, and if they are same, you are done, you can say equal. Okay. Okay, so we will stop here for this segment and we will come with some more example maybe, and some more concepts which are not that obvious with respect to vector.